In this video, we'll review inverse trig functions. So I want to begin with an example which says to evaluate cosine inverse of negative root 3 over 2. So when I see this notation on a trig function, this means an inverse trig function, in this case inverse cosine function. It does not mean like raise it to the -1 power. So this is not an exponent. It's not just 1 over cosine of the stuff. So how do we think about things like this? Let's recall that when we talk about the original function cosine, we plug in an angle into cosine. Let me call that theta. So we plug in an angle, and what we get out is some number, which I'll call r, and r represents a ratio of side lengths in a triangle. And what I want to be able to do is to be able to talk about the inverse of this function. So this should be equivalent if I think about the inverse function. And I'm going to denote the inverse function as cosine. I'm going to write this -1. And the inverse function should switch the input and the output. So now the output, which used to be r, will now be the input of the inverse function. And the input of the original cosine function is now going to be the output of the inverse function. Alrighty, so let's use that idea here. I'm trying to figure out what cosine inverse of this number is. So I'm going to let cosine inverse of negative root 3 over 2. I know now that the input of an inverse trig function is a ratio, and the output should be an angle. So this should be equal to some angle theta. And I can rewrite this in terms of the original trig function, cosine. So cosine, and now I'm going to switch the input and the output. So I plug in the angle, and the output is this negative root 3 over 2, that ratio. So I want to know cosine of what angle equals negative root 3 over 2. So let's go to a unit circle to help us. So I'm going to go draw my axes and then draw a unit circle. So recall that cosine is negative in quadrants 2 and 3. So remember that this is the first quadrant, this is the second quadrant, this is the third quadrant, this is the fourth quadrant, because cosine represents the x-coordinate of the point on the unit circle. And the x-coordinate can only be negative over here in quadrant 2 or in quadrant 3. So I'm going to draw a point in quadrant 2 and a symmetric point in quadrant 3. I'm going to connect those with the origin and then drop a vertical line to the x-axis to make my right triangle. And cosine needs to be equal to negative root 3 over 2. So my x-coordinate needs to be negative root 3 over 2. So this length, that horizontal x length, should be negative root 3 over 2. And the hypotenuse, remember, in a unit circle is 1, so that's 1 and that's 1. So hopefully at this point I can see that, oh, this seems to be a 30, 60, 90 situation. In fact, so the missing side length of this triangle is going to be a 1/2 here. This one also down up until this point, and then from here to the bottom, it's also a 1/2. But down there, that y-coordinate's negative, so I'll put a negative sign in front of that 1/2. Okay, now if I label the angle, this, let's zoom in a little bit more. This is 30 degrees. Similarly here, this is 30 degrees, and this is 60 degrees, and that is 60 degrees. So this point is the angle 5 pi over 6, or 150 degrees. This point over here is 7 pi over 6, which is 210 degrees. So I have... Alright, so I'm going to separate this a little bit to give myself some room. So theta could be, if I was at a place like 5 pi over 6, theta could be 5 pi over 6. But also from 5 pi over 6, I could start going around the unit circle. So if I went around the unit circle once in the positive direction, I would get 5 pi over 6 plus 2 pi. But also from 5 pi over 6, I could have gone around the unit circle in the opposite, in the negative direction, and that would have given me 5 pi over 6 minus 2 pi. I'll get the same thing, same type of thing if I were to go around the unit circle twice in either direction. Then I would have plus or minus 4 pi, and I could keep going like this, comma, dot, dot, dot. I would do plus or minus 6 pi and so on. Let's do the same thing for 7 pi over 6. I could get 7 pi over 6, as well as 7 pi over 6 plus or minus 2 pi from going around the unit circle once in either direction. 7 pi over 6 plus or minus 4 pi from going around it twice in either direction. So overall, there's an infinite number of possibilities for what theta could be. But that's an issue because we want cosine inverse to be a function. So when we plug in this ratio into it, we want that output, we want there to just be one output. So we want cosine inverse of x to be a function, just like cosine is a function. So we need just one output. So just one output. So we need a way to decide, well, which angle are we going to pick for the output? Okay, so to motivate this, I'm going to draw the graph of cosine. Y equals cosine of x. So let's recall what this graph looks like. So I'm going to draw some axes, make it a wide graph. And then the y-intercept of this graph is at 1. And then it starts going downwards. It gets as far low to a y value of -1. So this y value is at +1, this one's at -1. And then it oscillates on back up, reaches this high point again, and then tricks down. All right, so drawing it in the negative direction, it'll trick down and then come back up and oscillate like this. So we have the graph of cosine. And let me label a couple of the angles here. So it crosses this x-axis at pi over 2. And then it has this low point when the angle is pi. So next, I want to recall a key fact about when a function has an inverse function, and then use that and tie it into my cosine graph. So for a function to have an inverse function, it must be what's called 1-to-1. And graphically, a function is 1-to-1 if it passes the horizontal line test. Okay, so let's go back to our graph and see, will it pass the horizontal line test? So a graph passes the horizontal line test if any horizontal line that I draw intersects the graph at most one time. But with cosine, there's plenty of horizontal lines that I could draw, like this one, that intersect the graph way more than one time. So this does not pass the horizontal line test. It's not going to be 1-to-1. So to fix that, we will restrict the domain. We will restrict the domain of our graph of y equals cosine x to make it 1-to-1. In other words, we're just going to look at a tiny portion of the graph where it will pass the horizontal line test. So there is a convention when doing this, and I'm going to go back to the graph to state what that is, but we will restrict, there is a convention on how to restrict the domain. We will restrict the domain to, and now let's go back to the graph. So I'm going to limit myself to just a tiny portion of the graph where this will pass the horizontal line test, but I'd like it to be as big of a piece as possible. So the convention is to start it here, and then traverse it to the right until I get to this bottom point. I can't go any further than that, because if I go even a little further, it won't pass the horizontal line test anymore. So notice that we're starting at an angle of 0 and then going up until an input or an angle of pi. That's what we're going to restrict the domain to. So we will restrict the domain of the cosine graph to be just from 0 to pi so that it does pass the horizontal line test. And the domain of the original function is going to be the range of the inverse. This is going to be the range of the inverse function because the inputs of the original function are the outputs of the inverse. Okay, and then 0 to pi, these are the values of theta that we're limiting ourselves to. So with this idea in mind, let's return to the original question. Remember, we want to figure out, well, when is cosine of theta? When is that going to be equal to negative root 3 over 2? Where, and now we have this restriction on the values of theta has to be greater than or equal to 0 and less than or equal to pi. So let's return to our unit circle for this. So I'm going to draw it one more time. We'll have our axes, we'll have our circle, but we're limiting ourselves so that the angle is between 0 and pi, so that is just in this range of angles. And there was one triangle that satisfied this, that lied in that range. We had drawn it before. It was something like over here, I had a point, connected it with the origin, and dropped a perpendicular to make it a right triangle. And this horizontal length was negative root 3 over 2. The vertical length was a half, and the hypotenuse, or the radius, was 1. And we had seen before that meant that this angle was a 30-degree angle. And so the angle from where 0 is to this point is 5 pi over 6, which is 150 degrees. So thus, we now know what theta needs to be. Theta can only be 5 pi over 6. And that is our answer. That is what cosine inverse of negative root 3 over 2 is. So what I want to end this video by talking about is, well, we've shown how we restrict the domain for the cosine graph to get its inverse. But I want to just briefly talk about some of the other common inverse trig functions and how we restrict the domain for them so that they have an inverse. Okay, so for the other inverse trig functions, I'll do it for the most commonly ones, for the ones that most commonly show up, like sine and tangent. Okay, so I'm going to start with the sine graph. Okay, so the sine graph, its y-intercept is at the origin, and then it'll go up, have a high point, go down, have a low point, and then keep traversing up. Keep oscillating. On the other direction, has a low point, goes up, and it'll keep oscillating like this. And in this graph, this high point occurs at pi over 2. This low point occurs at negative pi over 2. And then this value would be at pi, and so on. And the convention for this, if I want to make this one-to-one, the convention is to start it here at this low point, and then to go until I reach this high point. And on that portion of the graph, it does pass the horizontal line test. So what I'll say is we will restrict, in this case, the domain to the interval from negative pi over 2 to pi over 2 so that we can define sine inverse of x. So let's show what it would look like for tangent. So for tangent, let's draw y equals tangent of x. Alrighty, so I'm going to try to squeeze this in here a little bit. So I'll draw in my axes. Tangent graph has a bunch of vertical asymptotes. So I'm going to draw in some vertical asymptotes, draw in those vertical asymptotes, and then in between each pair of vertical asymptotes, it snakes upwards like this, and then it repeats that shape in between each pair of vertical asymptotes. So that is the graph of tangent of x. So the convention for tangent graph and how to restrict the domain is we restrict it to this middle portion. Okay, so for this, we are going to restrict the domain to the interval from negative pi over 2 to positive pi over 2, but I can't include either negative pi over 2 or positive pi over 2 because tangent is undefined at both of those angles. So I have to put a parentheses at both of them. And that's what I restrict the domain to so that I can define tangent inverse of x as a function. So in our discussion videos, we'll do more practice with inverse trig functions, and I'll actually show, well, what do the inverse trig graphs look like? I'll do that for a couple of these. So in terms of our goals for this section, we finished the last part of goal 1, reviewing how to simplify inverse trig functions.